be below the static yield strength, of the material. When it is called as ice cycle fatigue, and the repeat application of the plastic strain, it is a low cycle fatigue. So the plastic yield strength is the criteria for the defining the high cycle fatigue and the low cycle fatigue. So the crack initiation features and striations will be coming, and those are the creep failures. If you look at that is the thermally assisted plastic deformation. Actually, whenever you talk about the high temperatures, and the creep failures will come, and whenever the material is put under the high temperatures, and most of the power plants, if you look at that, it is exposed to high temperatures, and this will be
Anand, Dr. Anand. Yeah, actually we see only first slide.
Pardon?
We see only first slide. So it seems you have moved already few number of slides.
Okay.
But we see only first slide. Can you please share once again the PPT?
So, is it okay?
Like, can you please move the slides, 1 or 2 slides? No, we see only first slide still.
Sunil, is it visible?
It is visible, but we see only first slide. You do one thing. Please close the PPT once again, and again share once again.
You want me to repeat again?
Yeah, no. We are unable to see. మనకి ఫస్ట్ స్లైడ్ ఒకటే కనిపిస్తా ఉంది. ఒకసారి PPT క్లోజ్ చేసి మళ్ళీ షేర్ చేస్తే ఏమన్నా స్లైడ్ మూవ్ చేస్తా ఉంటే we are unable to see. ఓన్లీ ఫస్ట్ స్లైడ్.
ఓ, స్లైడ్స్ కనబడలేదా?
స్లైడ్స్ మూవ్ అవట్లేదు. ఫస్ట్ స్లైడ్ ఒకటే కనిపిస్తుంది.
ఒక్క నిమిషం అయితే.
ఓకే. ఇప్పుడు మూవ్ అవుతుంది స్లైడ్.
Now it is okay, na?
Now it is okay.
Okay, I think it is some kind of the problem. Okay.
Yeah. Yeah, please go on.
So we are here actually. Three failures. So it is a thermally assisted plastic deformation, and when we talk about high temperatures, and these creep mechanisms will plays a major role there. And generally it occurs at 0.3 melting temperature of the materials, and to 0.4 melting temperature of materials. So whenever most of the power plants will expose to high temperatures, and these creep mechanisms will play major role there. So the typical example of this is the turbines. When you look at turbines in the power plants, and it is exposed to the creep mechanisms. So generally creep will forms voids at the grain boundaries, and that will be visible on the surface in the microscopic conditions. So that will indicate that the creep mechanism would have happened in the materials. So next, environmental failures, the corrosion failures. Because of exposure of the material to the environment, then this corrosion failures will occurs there. So it will occurs in uniform corrosion and pitting corrosion, selective leaching, intergranular corrosion, concentrated cell corrosion, crevice corrosion, and galvanic corrosion. This type of examples for this environmental failures. So mechanical environmental failures, the synergic action of tensile stresses and corrosion environment. Only specific environment cause failures. If you look at the examples of that and the season cracking, only specific environment will be creating the cause of failures. And the microstructural, alloy influence susceptibility, the sensitization, it will happen in stainless steels. And generally pure metals will not happen this type of sensitization. So if you look at transgranular and intergranular mode of the failures in this thing, and transgranular means it will happen through the grain, and intergranular means it happens in along the grain boundaries. So this is a basic difference between the transgranular and intergranular. So till now what we have understood is different types of failures and what are the how it happens and what are the what are the conditions for the failures and those type of things. What we learned here till now. Now we are going to see the application in the origin of failures in thermal power plants. Thermal power generally, I've taken up this specific area and the thermal power plant for this presentation. So I want to give some highlight on some thermal power plants, how it happens and what are the reasons for the failures. And when somebody is going for the jobs in thermal power plant, it will be much useful. And I want to give some knowledge base on this. There are two different ways these failures will come. The one is the fireside corrosion and the waterside corrosion. Fireside corrosion, if you look at the boiler, it is a series of tubes, and the water, the coal will be burned, and the water will be flowing inside of the tubes, in the boiler, and coal will be burned because of that heat. And that water will be converted into steam. That steam will be used for this running the boilers, running the turbines, and then subsequently you will get the electricity. That is the basic principle of that particular boilers. So the fire side is what I am talking about is the outside of that particular tube. And inside is I'm talking about inside of the tube. That is water is flowing inside. That is nothing but it is converted into steam. So outside is nothing but this flue gases. Whatever the coal burns, and it will convert the flue gases. It condenses and then it goes to the atmosphere by converting the water to steam. So if we look at the line diagram and then what we have explained, then ash will, coal will be burned here, and it touches to the boiler and then goes to different regions, and then and finally it goes to the atmosphere. So in this process, then what we are seeing is the two components. One is the flue gases path. Another one is the steam, different regions, which is comprising of different tubes, and how these mechanical components will plays a major role with respect to your flue gases and then water which we are using for these boilers. Those are the main variables there. The fire side corrosion is as for fire. It mainly deals with the coal which we burn. So it burns and then it attaches to the surface, and then it gives some sort of corrosion, and that corroding elements will degrade to the tube function. So if you look at the transport mechanism, the small solid particles of ash will carried by the flue gas, and it will attach to the tube outside. This is a tube. This is a tube. That the tube outside, and then it start corroding, and the boiler inside is the water will be flowing. So we are talking about the outside temperature, which is corroded by this thing. And over the time, the deposit will accumulate like like this, and then it progresses to some thickness. And this once we accumulate the thickness, and then the heat transfer from outside to inside will decrease. And then the heat transfer will be hindered by this ash on the outside of the tube, so that the efficiency of the boiler will come down, and as well as this ash will contribute to corrosion, and then it will damage the mechanical components there. And the fireside corrosion of the coke file burden, there are a series of, corrosive products will form with the temperatures, and which I have highlighted here. And alkali sulfates, the sodium potassium pyrosulfates, and with the temperatures it goes, and then it degrades the tube surface. And generally, fireside corrosion, if you look at, and generally, power plants will expect it to operate in the oxidizing environment. Oxidizing environment means oxygen should be there within the power plant. When it is ready, when it is turning out to the reducing environment, like sulfide SO4 environment, and FES and this FES2, and this iron sulfate will form. So that is not important. That is not, as far as useful for this running is concerned. This creates the reducing environment, and this will induce the corrosion in the materials. So always you try to operate the iron oxide, oxidizing environment. That is always good as far as this operation is concerned. So then next one is SO2 and S43 gases, and these SO3 and S42 gases will come from the coal burning, because the coal contains sulfur dioxide, sulfur. This with oxygen it forms SO2 and SO3 gases, and this will corrode the tube surface. So there are so many areas which will be affected by this fireside corrosion, and one is superheater tube region, and based on the temperatures and which are given there, which are given earlier slide, and that this deposits will form and then corrode the surface. And chlorine also should maintain low level, and the coal, so that it corrodes the tube surface. And it forms sodium, potassium, iron sulfates, and on the tube surface, and then it degrades the tube very fast. And cold end corrosion, for example, there are certain regions will be there, evaporators and condenser and all things, and these are the cold end regions. And the gaseous, hot gases will come and deposit and due to the condensation. And while condensation, these SO2 gases from the flue gases will condense on the tube surface, and which HO2 is also there. HO2 is also from the steam, inside the steam. It is the moisture will be there. And with the moisture, and it warms the H2SO4 acid, and whenever the acids are there, then the surfaces will corrode faster. So this mechanism should be avoided as far as this is concerned, and it should be always that the dew point pressures and temperatures and controlled in such a way that, and this mechanism should be avoided. And finally, if you conclude, and the waterside corrosion is due to the water quality and dissolved salts and pH, etc., and oxygen pitting and galvanic coupling and changification and corrosion fatigue. So these are the waterside borne corrosion, and what we do actually, the role of NML. What we do in our organization, and what I'm doing by sitting in NML. So I am finding out the root cause of the failure of the component with respect to the component materials point of view, and operational condition point of view, and raw materials and coal feed point of view, and remaining life assessment studies. So as far as this sector is concerned, so I am doing for the so many sectors, and which I am presenting is power plants. And we have touched so many components as far as boiler is concerned, and we have touched water side, water wall tubes, and boiler bank tubes this place, and we have touched reheater tubes, and we have touched condenser tubes, and we have touched LP rotor turbines, and we have analyzed all the components as the national projects. And first, I want to share the one case study which we have presented, which we have done it for the Hindustan Zinc captive thermal power plant. And it is this material. I mean, this failure is like a fish mouth failure. And what we are seeing is this is a typical steel, low carbon steel. And if you look at the microstructure, there is a brown color area, brown colored and then black color areas. We would able to see that it is the two. I mean, on the fire side, it will be of corrosion deposits, and water side also we are seeing the deposits, which I mean, yellow color deposits and brown color deposits. That is also deposits. And as far as the microstructure is concerned, and we are not experienced any sort of degradation in the microstructure, and it is intact. And as far as when we talk about the microstructure, then I say that I mean nothing was happened, and whatever the degradation is happened is the surface. Then we have focused on surface, and we have highlighted the fire side what are the elements, and water side what are the elements. And fire side we could able to see the copper. I mean much of the copper. Actually, I mean we could able to see iron oxide and elements which are contributing from the coal ash. Those things are contributing, which identifying that it is due to the ash components also playing major role there. And the water side, I could able to see the copper. Copper is, I mean, why this copper is coming and depositing on the iron surface, because I mean generally iron surface should not have copper. And the copper is coming means, I mean, that copper and iron have the tendency to the form galvanic coupling. So that with that approximation, then we have gone through the analysis, and still we have gone inside the microscopy level, and then we have scanned this thing. I mean, the deposits on the damaged region in the micro level. So what we are seeing is the copper is presenting at the higher level, and then it is creating galvanic coupling with the iron surface. So with that we have one say if you see that the region which we have seen on the surface is copper rich and copper unrich regions. That indicates that the galvanic coupling is happened. So with that approximation, we could able to reduce the mechanism why it is happening and other things. So then we have given the mechanism for the material degradation, and then finally this final equation should be avoided. For example, I mean CuO, I mean copper oxide should be the formation of copper oxide should be the avoided. So for that, what we have to add complexing agent, and then to avoid the copper oxide, and then the copper remains should be the copper chloride, and the iron should be the iron chloride. So that this corrosion will be delayed. So that it will run. The degradation, whatever it is happening, what is happening is we can avoid. So then finally, what we have decided is that this tube is failed due to the galvanic coupling in copper and iron, the localized degradation of tube from the water side of the tube, and ash formation, ash corrosion on the fire side has also controlled to the failure of the tubes. So there are two. Water side is failed due to the galvanic corrosion, and fire side is failed due to the ash corrosion. Those are the two reasons for the failure. And we have even published in international journal, so engineering failure analysis, and the same result. So next, I am going to present these water wall tubes, and these tubes are generally exposed to high temperatures, and it is exactly like a fish mouth. So this we have done it for the local power plant. And if you are able to see that there are the cavities around the fracture region. That earlier what we have seen that creep when you identify this, the creep voids will be there. So those type of features we identified. That with that approximation, we can say that it is the creep is operating mechanism here. So optical microscopy also we have carried out, and then there is the pits in the microstructure. We have seen that. Then the internal microstructure is also damaging very fast. And we have even see the microstructure of the steel. I mean, this is the microstructure of steel. So then the microstructure is generally perlite and ferrite should be there. So good microstructure. When it is exposed to high temperature, the decomposition of the perlite is happening. Decomposition means, I mean, perlite will be, it will be like this. And perlite is nothing but ferrite and cementite, lamellar-like structure. But when it decomposed and the perlite is totally disintegrated, and then it will be turning out to the ferritic microstructure. So the fracture surface, what we have seen is intergranular microstructure. It shows that the ductile mode of failure. So, and what we have observed is the elements which we have taken from the EDX, and we have observed that this ash corrosion is the main corrosion there, and deposit has been accumulated, and then it hindered the heat transfer from the outside to inside temperature inside the tube, and due to the temperature accumulation, then short-term overheating has been applied on the tube surface. So finally, this tube damage has been occurred. So that is what the conclusion is. Next, the case study 3 is LP turbine blade. What we have done it for the Ennur thermal power plant, Tamil Nadu. So generally, it is designed to run for the 1 lakh hours, but it is done for the 9,341 hours only, and it is a premature failure, and we have gone for the analysis. This is the small component which they brought it to us, and this is the small piece, and with that piece, then we have identified the failure, and then the location of the failure, it is schematically given here. And if you look at the surface outside, surface that the erosion is happening there. Erosion is due to the steam heating. Steam heating, particles are hitting, and it is damaged on the surface. So if you look at the fracture surface and where we have to identify the origin of the failure, where the failure is originating, and we have taken that region, and we have identified the region, and then the fractography is carried out, and we have identified the beach marks. Beach marks is a characteristic of fatigue failure because of the cyclic loading. So that we have identified. So even the microstructural features also were identified, and then the chromium carbides has been formed because generally tempered martensite, the chromium carbides are forming means that material would have exposed to high temperature. That is the indication. So that should not be that should not happen, because what we have seen the season cracking, sensitization. So that type of problems we have seen here. So sensitization problem here in the stainless steel. So it is a typical steel microstructure, but the chromium carbide should not be allowed due to the rise in temperatures. So pits EDAX analysis we are taken up, and then this we could able to see the chlorine which higher level, and with this chlorine, then we could able to see that the chlorine induced corrosion and the pits are forming here. These pits can the fatigue mechanism is operating, and these pits can facilitate the failure to be opened, that fracture surface to be opened. So that is what happened in that particular case. This here we are seeing the both the fatigue as well as corrosion. So with this, we can say that it is due to the corrosion fatigue. So whether what is the real cause for, I mean, for example, we are talking about turbine failure and turbine blades failure, and why it is happened. So we are taking the different regions, I mean, in the power circuit, the power plant circuit, and we are taking the water, I mean, inside water flowing, and we have gone for the analysis, and we could able to see the chlorides which higher percentage in different regions. I mean, which the steam is going to the turbines. So that indicates that the chlorine is going to the higher level, and then that is creating damage to the turbines. And chlorine in this aspect is 29. I mean, deposit accumulated on this turbine blades also we have taken out, and then we have gone for the wet chemical analysis of that particular this thing, and we could able to see that the chlorides will be of dominating elements, then which indicates that the chlorine is damaged at particular surface. And operational data analysis also we have done, and then and some abnormalities with respect to operational, then that is also catalyzed for these failures. Abnormalities means, I mean, if it is a peak, I mean, if it is the peak, then it should be uniformly it is distributed. But if we are seeing the big peaks here, so that means the operational parameters has been deviated. So I mean, due to the higher, production and all things, they would have operated, and that would have facilitated that turbine blades to be failed at that particular region because of that this. So conclusion: turbine blades fail due to the corrosion fatigue, and then it is due to, I mean, operational parameters telling that the excessive inlet pressure of the steam to the turbine, and moreover the steam containing more chlorides. So this corrosion fatigue is the major problem, and we have even published this aspects in this in the Journal of Failure Analysis and Prevention. So one more, this is the final case study what we are presenting here is and reheated tubes. We have done it for the Neyveli Lignite Corporation power plant in Neyveli, and the reheater actually it heats the, I mean, it heats the raw water, I mean water in the power, I mean cold water is coming here, and the steam, I mean, that steam which is coming out, circulating in the boiler, and waste steam is coming, I mean, coming out, coming inside, and then it is like a heat transfer, I mean, heat capturing mechanism, and waste from heat recovery boiler. It is like a heat recovery boiler. So heat, I mean, the steam will be coming, and then that steam will be captured by the water which is circulating inside this reheater tube, and this is the basic function of that particular reheater tube. So generally this is the stainless steel. So that the material specification is given SA213 TP316, and this is the failed tube which has come to us for the analysis. And we could able to see the longitudinal cracks on the tube surface. And the internal stereo microscope is showing that the cavities on the internal surface. So that means, I mean, we have to focus on something under some cavities, why it is happening in this area. So then I could able to see the cross-sectional tube thickness cross-sectional images. Then I could able to see the cracks which is trenching towards the thickness. So that, and branching of the cracks also, I mean, it is given here. So that means, I mean, some mechanism is operating there, which it is still known, and then still unknown. Then we have to go why it is happening. So then we have taken microstructure at the, I mean, the inside microstructure, and where exposed region, and we could as deformed microstructure. Deformed microstructure means I can able to say that stress is operating there. Some stress is created deformation in the microstructure. So that is one of the confirmation I got. And the microstructure, what we have seen inside, and the intergranular corrosion in the microstructure. So this shows that intergranular corrosion in the material, and even branching of the micro cracks also I have seen that. And I could able to see this the calcium. I mean, if you see this SCMMEE analysis, I could able to see the maximum of calcium. This calcium is actually one of the corroding element as far as steel is. I mean, this particular this thing is concerned. So finally, we have even seen that why calcium is more, and sodium is also, and so many elements which is carried by the water and corroding elements we have seen here. That means the corrosion is happening from the water side. So finally, the conclusions, and as with respect to the HP heater is concerned, we have seen the stress is damaging the microstructure, and the corrosive element is responsible for this damaging the microstructure, damaging the tube surface. With this indication, we can able to say that the tube is failed due to the stress corrosion cracking. So that is the indication of that particular tube is concerned. The accumulation of caustic in the sense it is a calcium and sodium was regulate the generally these elements will be added for the pH control. So when they add the more amount, and when the concentration of that particular elements in this water is more and getting more, then this type of problems will become. So then this is a purely operational problem. That has to be modified. So this particular work we have published in Engineering Failure Analysis in 2018. So the final conclusion is the failures in the water side of the tube is due to the feed water quality, and failure generally what we have seen in two case studies, and failures on the Fireside Corrosion tube is feed coal quality. Coal is whatever the coal we are using in the burning, and that has to be monitored. And failures in turbine blade is due to the steam quality, and turbines which is failing means some steam should be of good quality, and if it is deviating, then this type of problem will come. And the operational parameters should be within the design limits of the boiler. And generally, I want to emphasize and the research gaps here. And what we are seeing is there are so many problems we have seen in the power plants. What are the problems we have seen is different corrosion, and then from the water side or flight side. So the research gaps which we can able to focus is different material development, different materials development here, and different coatings. For example, without increasing the material cost, and different coatings can be focused to improve the performance of the boiler, and then to mitigate this type of corrosions in the boilers. So that can be highlighted and focused on that particular. I hope this my talk will enrich some knowledge base as far as mechanical area is concerned. Thank you very much.
Yeah. Thank you, sir. Thank you for the wonderful presentation and giving good insight in the failure mechanisms in power plant, totally related to the mechanical engineering stream and the metallurgical stream. And I thank you once again on behalf of ICMMEE 2021, and I believe the participants